So this is ELC131, Circuit Analysis 1. In this presentation, we're going to look at applications of transformers. Now, there's four general applications of transformers. They are to step up voltage and step down current, to step down voltage and step up current, to provide electrical isolation, and to perform impedance matching. Now, referring to figure 1, we see the generation of electrical power at the power plant, a step-up transformer, a step-down transformer, and another step-down transformer. And again, this provides us a good illustration or an example of the use of step-up transformers. So at the power plant, we generate electricity at 12 kilovolts. Now that voltage is stepped up to 400 kilovolts to send along the high voltage transmission lines. And the reason we do this is, of course, if we step up voltage, we step down current. So the current through the high voltage transmission lines is reduced. Therefore, we reduce the power loss along these transmission lines. And this also allows us to construct these transmission lines with thinner and, of course, lighter wires. So this reduces the cost of the wires themselves, and it also reduces the construction cost of the towers used to support the transmission lines. The lighter the towers, or the lighter the wires, of course, the smaller the transmission line towers have to be. So again, we use a step-up transformer to increase the voltage from produced at the power plant to a high voltage level for transmission over long distances. Now, once this high voltage gets to our cities and towns, we need to step it down to a lower level for distribution through the town and through the neighborhoods. So we use a step-down transformer at a substation to step this 400 kilovolts down to a level, for example, 13 kilovolts. Now, of course, when I step down the voltage, I can step up the current. So from the substation through the neighborhoods, towns and neighborhoods, we have a lower voltage level, but we have higher current through the power lines. Now, when we get close to our houses and or businesses, we use another step-down transformer to step this voltage down to 240 volts for our houses. And I want to take a little closer look at a utility pole transformer. Now, you've all seen these utility pole transformers. They're a big gray can that hangs on the wooden pole outside your house or your business. And we also see these as the big green box that sits on the ground if you have underground service in your neighborhood or subdivisions. So for this example, we assume that the voltage on the power lines is 4.8 kV. And we use a step-down transformer with a center tap secondary to provide 240 volts to our homes to power the water heater, the electric range, the heat strips for our HVAC system. And of course, the center tap allows us to have 120 volts for the lighting and receptacle circuits in our homes. Now, I'll point out, if you note looking at figure 2, that there are multiple taps on the primary of the transformer. And this is done, of course, so that if the power line voltage is 4.8 kV, we'll use the tap that gives us 2,400 turns in the primary. However, as we go along the power lines, the further we get from the substation, we'll find that the voltage on the power line gets smaller and smaller. Because of course power lines have resistance like anything, and as current flows through the power lines, we'll see a reduction of voltage along the power lines. So as we get further from the substation, the voltage on the power line may be smaller than 4.8 kV, so we would need to use one of the other primary taps, such as the tap that gives us 2,292 turns or 2,184 turns, so that we always obtain 240 volts at the secondary of the transformer. Now, another application for transformers is to provide electrical isolation. So, referring to the diagram in figure 3, notice that we have a voltage applied to the primary of the transformer. And one side of that voltage source applied to the primary has a connection to the earth. This is the earth ground schematic symbol shown. Now, with our isolation transformer, we have a 1-to-1 turns ratio, meaning that NP equals NS. Therefore, VP equals VS. So if I apply 120 volts to the primary, I'll obtain 120 volts at the secondary. But note that the secondary voltage does not have a connection back to ground. And what this does is it provides electrical safety for someone that comes in contact with the secondary winding, that there is no voltage difference between the secondary winding and ground. So you can safely touch this circuit and not have a connection, a path for current back to ground. So the electrical isolation is provided to provide electrical safety. Now, these isolation transformers are used when servicing and repairing electronic circuits. Quite often the chassis of a piece of equipment is connected to ground when it's plugged into a receptacle. However, when using an isolation transformer, this now means that the chassis of the electronic circuit or device that we're repairing does not have a physical or electrical connection back to ground. So this offers us some level of safety in that we can touch the circuit and not have a path to ground via the chassis if we were to touch a energized point and the chassis at the same time. Now, isolation transformers are also widely used in hospitals. And the reason they do this is that if we have, for instance, a hospital bed, which is, as you know, motorized, plugged into a receptacle, the chassis of that bed could be elevated at some voltage above the earth. And if we plug another piece of electrical equipment, such as an infusion pump, into a grounded receptacle, then there could potentially be a difference in voltage between the chassis of the bed and the chassis of the infusion pump, therefore creating a potential for current to flow through someone that was touching both pieces of equipment at the same time. So quite often, I shouldn't say quite often, but in hospital rooms, they will always provide isolated receptacles, again, that are obtaining their voltage through an isolation transformer. So there is not the potential for the chassis of two pieces of equipment to be at different potentials, because the chassis of the piece of equipment plugged into the isolation transformer has no electrical connection to ground. This will be quite important if you find your career or find a career in medical electronics. Now, the last application we'll look at for transformers is for impedance matching. And before we talk about impedance matching, we need to define impedance. Impedance, symbolized with the letter Z, measured in ohms. The unit symbol is the Greek letter omega. And impedance is the opposition to alternating current. Now, the maximum power transfer theorem states that maximum power is delivered to the load when the impedance of the load equals the impedance of the source. So we refer to the circuit of figure 4. We see an AC source with a source impedance of 600 ohms driving an 8 ohm speaker. Now, we won't go through the math, but hopefully you can recognize the fact that the majority of the power is going to be dissipated in the source resistance and not in the 8 ohm speaker. And this is contrary to what we want to have happen with an audio system. Of course, we want to deliver maximum power at the speaker to deliver or to obtain maximum acoustical power. So the solution is that we use an impedance matching transformer to make the 8 ohm speaker look like it's 600 ohms. Therefore, we will satisfy the maximum power transfer theorem, that maximum power is delivered to the load when the load impedance and the source impedance are equal. So again, the matching transformer is used to make the 8 ohm speaker look like it's 600 ohms. So in figure 5, we see this circuit constructed with a transformer between the circuit and the 8 ohm speaker. Now, mathematically, the turns ratio of the matching transformer, NP over NS, equals the square root of the source impedance over the load impedance. So we substitute in the values given for the source impedance and the load impedance, 600 ohms for the source impedance and 8 ohms for the load impedance, and we calculate that we need an impedance matching transformer with a turns ratio of 8.7 to 1 in order to make that 8 ohm speaker look like it's 600 ohms and thereby delivering maximum power to the speaker. Now, we see fewer and fewer instances in particularly audio systems that utilize impedance matching transformers. In today's world of integrated circuits, we can build chips that can drive that can drive 8 ohm speakers without the use of impedance matching transformers. But for old audio systems, you'll still see audio matching transformers used in high-end, or not even high-end, but in audio amplifiers. So we've looked at the applications of transformers to step up or step down voltage, and of course step down or step up current to provide electrical isolation, and also for use in impedance matching.